what do we do? So I was given the title Supercuspidal Representations, Construction, Parameterization, Classification, something of that sort, and character formulas. So that's what we do today. And we start with the construction, but I want to give a clarification first from last time, which is something that I said at the beginning of the Q&A, but I'm not sure everyone heard this. So last time, what did we do? I started the lecture by starting with pairs consisting of an elliptic maximal torus and the character of it, either in the real world or in the p-adic world. Well, in the real world, if we want to get all discrete series, we also in general have to take a subsystem of positive roots. But if we assume that theta is sufficiently regular, then this is automatically determined by the rest. And to that, we then attached a representation pi sub s theta, which was either a discrete series representation or essentially discrete series representation if the field was R, or it was a regular supercuspidal representation if the field was a finite extension of QP. And since I talked about parameterization, I just wanted to add the fact that I said in words that two representations attached to one pair, attached to another pair, another torus, another character, are isomorphic if and only if these pairs are conjugate. So if and only if these two pairs are GF conjugate. So that's then how you can actually parameterize all the representations, all the discrete series representations. Well, then you have to take the triples, all the regular supercuspidal representations using this data, and that you know they are isomorphic if and only if the data is conjugate. And what we want to do today is construct not just the regular supercuspidal representations, but all supercuspidal representations from a certain input, and then also try to understand which input gives us the same representations, and then in the end, state character formulas. So the way I motivated the story is that last time we saw that even for the real world and the p-adic world are very different, we somehow obtained the same character formulas. That was the big magic. All right, so let's see, what's the notation? So from now on, the notation will be that F is a non-Archimedean local field. So finite extension of QP or the Laurent series over finite field, which contains a ring of integer O, contains a uniformizer pi, and the residue field is FQ of characteristic P. So same notation as in the second half of last time. And for simplicity, I want to assume today that my group G, which was a connected reductive group, is semi-simple. So that's a semi-simple connected reductive group over this local field F. And you don't really need to assume semi-simplicity. It just makes certain things easier for me to write. So I don't have to always say compact mod center. I can just say compact, for example. All right, so that's the notation. So what did we do? What did we do last time? So last time, this is the first part of what we did last time. And then the second half of what we did last time is that I said in order to construct supercuspidal representations, there's a folklore conjecture that all of them are induced from a compact mod center, but now we can assume compact, open subgroup. And so we started studying compact open subgroups via the Moy Prasad filtration. So we started with the Bruhat Tits building. Oops. Curly B was the Bruhat Tits building associated to our group. So I said that I told you how to give data that parameterizes points in here. And then once we've chosen the point, we obtained from there Moy Prasad filtration, GXR for R being some non-negative real number, which was a compact open subgroup. And so today we want to use these compact open subgroups to study the representations of the group G of F. So, and I hope everyone did the homework to work out examples so you feel comfortable with them. So the first definition is the depth, so let pi v be an irreducible smooth, and I will not write smooth again, most likely. So all representations are smooth as last time. An irreducible smooth representation of our p-adic group G of F. Then the depth is an invariant that we can attach to this representation. And the depth is defined as follows. The depth is the smallest non-negative real number such that if we look at the representation space and look at the fixed vectors under the R plus filtration subgroup, so the filtration subgroup at a point x of depth R plus a very tiny epsilon, then this should be non-zero for some x in the building. So that's the notion of the depth that Moy and Prasad introduced in the 90s to give a first invariant to a representation. And then what they did is they studied also the depth zero representations. So let me do this as the first example. So let's now try to construction of supercuspidal representations. And so the first case are the depth zero representations. So how can
it be not integer? Is that?
Sorry?
Can it be non-integer?
Can it be a non-integer? Yes, the depth can be a non-integer. It's a rational number in general. So we will soon see an example of a representation that has depth 1/2. Excellent question. So the question was if it can be a non-integer. All right. Yeah.
So does the depth always exist?
Does the depth always exist? Yes, the depths always exist. Yeah, it's semi-continuous, this notion, so you can show that it always exists. All right, so let's talk about the depth zero representations so that you see a first example of representations. You actually have already seen some in Vitek's talk, a special case. So what is the input for depth zero representations? The input is the following. So we take a point inside the Bruhat Tits building of our group that is a vertex. So for example, if our group is SA2, say the field is QP, or maybe even more specific, say the field is Q3, then the building is a tree of valency 3 plus 1, so valency 4. So that's the tree. And we take a vertex, so we could take this point x. And then, so that's the first part of the input. And the second part of the input is that we take an irreducible representation of G sub x, which is how I denote the stabilizer inside the whole group of the point x, with the following properties. An irreducible representation that is trivial on Gx0 plus. So that is what turns it into a depth zero representation then in a moment, because it's trivial and it has fixed vectors under 0 plus here. It will have fixed vectors. So we want an irreducible representation. Oh, I should give it a name. Say rho of the stabilizer is trivial on Gx0 plus, and such that if we take this representation and restrict it to Gx0, what we defined last time, this is also called the Power-Horic subgroup, then there's a representation of the quotient because it's trivial on Gx0 plus. And well, what is this quotient here? So then one nice property of the Moy Prasad filtration is actually that the zeroth quotient of this filtration, these are always the FQ points of a reductive group. And all other quotients are abelian or vector spaces. And so that's a reductive group. So that means it makes sense to us if this representation is cuspidal or not. And we ask that representation to be cuspidal, such that this representation is cuspidal, or sum of cuspidals. So that means it doesn't have fixed vectors under unipotent radicals of proper parabolic subgroups. And so when you take such a representation, well, what is, just for example, this quotient here, gx0 mod gx0 plus in the example above is just equal to isomorphic to SL2 over the residue field, so that's FP up there. So you take a cuspidal representation of SL2, FP, inflated to gx0, then you extend it to the whole stabilizer, which in that case, in this example, gx will be just SL2 of O, of ZP. And then you have the input that you need, and then the construction. So the construction then is that you just compactly induce this representation. So you compactly induce from the stabilizer to the whole group your representation rho. And then this theorem, I guess that's due to Moy Prasad and independently to Morris, is that in that way you obtain an irreducible and supercuspidal representation. So the compact induction from Gx to Gf of rho is irreducible. Hence, by the fact that I stated last time, it's supercuspidal. It's an irreducible supercuspidal representation. And moreover, all depth zero representations arise in that way. Moreover, all supercuspidal, irreducible, depth zero representations arise in that way. So here's a representation, here's a supercuspidal representation, and all depth zero representation arise in that way. And that was solved around the 90s. So that's something we know since around the 90s.
Yeah, Jessica, you also know when two of them are equivalent or not equivalent, right?
You also know when they are equivalent, yes. And
so that the data X row are conjugated.
I have to. So in general, it's more complicated. For the supercuspidals, I think it's actually just when these are conjugate. I have to double check in general. Moy and Prasad, they define an equivalence relation for general depth zero representation that tells you when they are equivalent. Yeah, here it should just be conjugation.
Could I ask why does it happen that x's which are not vertices kind of don't matter for this?
So I'm asked, why does it happen that vertices that points in the building that are not vertices don't matter? Well, they do matter, but they don't give you supercuspidal representations.
Oh.
And for now, I want to focus on the supercuspidal representations.
Question.
Yes.
What's the relation between Gx and Gx naught?
What is the relation between Gx and Gx naught? So in this baby example, they are actually the same. In general, Gx0 is a finite index subgroup inside Gx for semi-simple groups. For reductive groups, you also have to take the center into account. So for example, if you take the point in the middle here for PGL2, Gx0 would be an index 2 subgroup in Gx. But for semi-simple, simply connected groups, Gx0 is always equal to Gx. So you can just think of Gx0 if you like. All right. So that's the depth zero story. Let's go beyond depth zero. And so from now on, I want to assume, to make my life easier, from now on, I assume that the group G splits over time extension of our ground field EMF, so say E over F some time extension. Sorry if you can't see it, it's just E over F should be a splitting field. I'll rewrite this again when we need it. And we assume that P doesn't divide the order of the Y group. So as we seen last time, these two conditions imply that all the supercuspidal representations arise from JKU's construction. So I'm actually able to tell you how all the supercuspidal representations look like. You can do the construction more general, but it just makes certain things easier for me to write. All right, so let's go deeper down. So that was depth 0. Now we want to have positive depth. So to go into the positive depth realm, I have to introduce some key notation that are used in the construction of supercuspidal representations. The first one is a twisted Levy subgroup, so G prime inside G. The subgroup is called a twisted Levy subgroup. If it becomes a Levy subgroup over some field extension. So if, well, I can just go all the way up to the separable extension to make my life easy. If the base change to the separable closure to a separable closure is a Levy subgroup. Usually one works with tame twisted Levy subgroups, but my assumption that P doesn't divide the order of the Y group makes everything tame. So that's one simplification. So for example, let me give you an example to keep in mind. So if G is SA2 of QP, my favorite example to carry around, you can take as G prime the groups that satisfies that G prime of F, or more general F prime, are the matrices of the form A, B, P times B, A inside SA2 of F prime. And so in particular, G prime of QP, when you adjoin the square root of P, you see that you can diagonalize these matrices, so this becomes just diagonal matrices. And that means over quadratic extension, this becomes isomorphic to a Levy subgroup, and that's why it's a twisted Levy subgroup. But over the ground field F, it's something compact. It doesn't look like a Levy subgroup, but it's a twisted Levy. So that's the first notation. And then the second notation is, so for the construction of supercuspidal representation, there are two inputs. The first input is the depth 0 theory that I've shown you, which is the representation of a finite group of Lie type here. That's the representation of a finite group of Lie type. The second input are nice characters. You kind of have seen that already when I started with acid torus and theta nice character, except I've never told you what nice means. So I'm going to tell you now what nice means. And when you see this the first time, it might be a bit scary, but I don't want you to be scared. So try to follow it, and if you don't understand the details at first go, you can still follow the rest of the talk. I also have written up a different version in my notes that you can look at afterwards, and it might take some time to get used to it. But so the essence is it's just the notion of regularity. So having said that, let's define it. So a character, let's call it phi of my twisted Levy subgroup. So now I want G prime inside G to be a twisted Levy. And I want to define a character of G prime. And a character of G prime is called G prime generic of depth R, where R is some positive real number at a point X inside the building of G prime. If the following happens, well, it should be first of all a character of depth R. So I want that phi restricted to G prime X R plus is equal to the trivial character. So the only interesting thing, or the first interesting thing happens at X R. It's trivial at depth R plus. And so what do I want it to do at depth R plus? Well, I think I need more space, so let me move over here. If this holds, and moreover, so let me first draw your picture to give you some intuition. So let's say this is G And inside there I have a, let's say, a Levy subgroup. So that's my Levy, say. So this is my G prime. It's, say, G is SLN, and G prime is now GL smaller Ln times the bunch of G1s. So that's my G prime. And now I want to define a character of G prime. So where can this character be interesting? So first of all, on G prime, on this box here, on this factor of GLN, the derived group of GLN, it basically is trivial. Characters are trivial on the image of the simply connected cover of the derived group, at least if the group is not anisotropic. So here it's trivial. So the only interesting thing is what can happen here. And on these GMs, on these copies of GMs, we wanted to be as generic as possible. So we basically wanted to have depths R everywhere. So we wanted to be as basically corresponding to a regular semi-simple element of depth R here. So that's some of the intuition. So let me make this precise. So we want that for every root alpha, that is a root of G with respect to, say, T is maximal torus of G prime that splits over some tame extension E. Well, I shouldn't have called it E there. Now I want the E actually here. So that's a maximal torus over which it splits. And this means absolute roots. So this means phi of G base change to the separable closure always. So when we look at all the roots of the group G that are not roots of the group G prime. And then we want to say essentially that, so what is this part here? This part is the image of precisely these co-roots, of the image of the co-roots of the roots that are not in G prime. Because if we are in G prime, we are here, and this is the part outside. And so we want to say that the character phi should be trivial on these co-roots of depth R. So we take here the R's filtration subgroup. So this is equal to 1 plus pi e to the ER rounded down times OE, where E is the absolute ramification index of E over F. And if you did your exercise, you might have encountered that. So that's the R's filtration subgroup. So we know that the character is trivial on R plus here because it has depth R. So we saw over there it's trivial on R plus. So the first occurrence where it can be non-trivial is at depth R here. And so for it to be generic, we really want this to be non-trivial. That's what it means to be generic, except, well, this root is only defined over the field E, but this character is defined over F, so I have to take the norm map down from E to F to make sense of that statement. So that's what it means to be generic. So it should be non-trivial at depth R everywhere outside here. So it takes some time to get used to it if you haven't seen that before. As I said, if you don't grasp all the details, you can still understand the rest of the talk, and you have time afterwards to think about it in more detail. So let me give you just an example. My favorite example is if G is equal to SL2 and G prime is over there. So let me just say these are A, B, P, B, A inside SL2 F. Then an example of a generic character is the following phi that takes a matrix A, B, P, B, A and sends it to, I have to introduce something new, 2 times B phi. What is phi? Phi I want to fix once and for all. Phi is a map from F to C star. It's an additive character such that phi restricted to O is non-trivial and phi, oh, sorry for that. I guess you can't, sorry, let me write this here to the notation section so everyone can see it. So phi is an additive character. Phi restricted to O is non-trivial. Phi restricted to pi O is trivial. So that's just my way to go from the field F, the p-adic field, to the complex numbers. And so one example of a generic character, and that requires some exercise, some work, some sitting down to see that this is generic, is take this matrix and send it to 2B and then apply this additive character to it. So that is generic of depth 1/2.
This P here is omega.
This P is omega. Yes, because in the example, yes, sorry. I'm carrying around the example with F being QP. I haven't written it down. So this F here is QP. Yes, so this is var pi. The question was if the P is var pi, and yes, this P is the var pi.
Do you require Z prime to become the Levy subgroup over a tail extension of n?
Yes, in general, we require the Levy subgroup. Well, what it means in general. For use construction, you require it to become isomorphic to a Levy subgroup over Tail extension. But my assumption that P doesn't divide the order of the Weil group makes this automatic. So that's the notion of a generic character. Now we want to use it to construct representation. As I said, just think of generic as regular as possible.
Sorry, it's not equal to 2 in our example?
Yes, so I said P doesn't divide the order of the Weil groups. In particular, P is not equal to 2. Yeah. That's important. Thanks. So the question was if P is not equal to 2. All right, so let's see an example of a positive depth representation. Well, that's a bad way of writing it. Of a positive depth representation. And this is then the combined with the depth 0 representations, we can then somehow get all representations in the end with a bit more work. So what should be the input? The input should be 2 things. I want a twisted Levy subgroup. I want a particular one to make my life easy. I want S to be an elliptic maximal torus. So that's definitely a twisted Levy subgroup. It becomes a torus over some field extension. And what else do I want? I want a character phi, a character of my group that is GS generic, say, of depth R. So that's my input. And then, well, also to make things nicer, or before I write this, let me make one comment. So that actually, since S is an elliptic maximal torus, that means S is a compact torus. So that means actually that the building of S, this is just a point. Because I said buildings are there to classify maximal compact subgroups. And well, if S is compact, there isn't much you can do. There's just one maximal compact subgroup. So in the example above of SA2, the torus S equals G prime, this A, B, P, B, A, corresponds to this point here. So this would be the building of G prime. And so that means it's just a point, and so I can also call this X. So that's a point that lies inside the building of the whole group G. So an elliptic torus determines a point. And now I want to make an assumption to make my life easy. And I want to assume the following. I want to assume that if I take my filtration subgroup of the group G at the point x of depth r over 2, where r is the depth of the character, I want this to be equal to the filtration subgroup of depth r over 2 plus. So I don't want there to be a jump. I want these two to be equal. So for example, this is the case in the example over there. I'm getting there in a moment. So I want to make this simplifying assumption. And then, hence, that means that actually if I look at the commutator of gxr over 2 with gxr over 2, this is the same as, by my assumption, the commutator of gxr over 2 plus with gxr over 2 plus. And now there's some nice property of these commutators of Moy Prasad filtration is that if you take the commutator, the depth adds up. So this is actually contained in gxr over 2 plus r over 2 plus, so it's contained in gxr plus. Sorry for those who can't see it because of the camera. And this means, therefore, we can extend the character phi, to a character, let's call it phi hat, of the following group, of the group, well, it is a character of this compact subgroup SF, and then we can extend it to gx r over 2 by asking it, well, it is a character that is trivial on depth r plus, it's trivial on sxr plus, and so it makes sense to then say that, oh, we just ask it to be trivial on the root groups of G outside S, essentially. So we just set it everywhere they're trivial, and it all makes sense because the commutator of two elements here lies inside depth r plus, so it makes sense to set it trivial there. So this is the largest subgroup to which we can extend it. And let me call this subgroup K. So that's just, in other words, extend as far as possible. That should be the slogan, what I'm doing. Just extend the character as far as you can naturally extend it. And now, then, if we compactly induce from this compact open subgroup to the whole group this character, then this is an irreducible supercuspidal representation. Of depth I. Well, it's gone now, the blackboard. So this will be a representation of depth R, so positive depth. So that's an abstract example, and I will give you now a very explicit example. Let's stop erasing here for a moment. So, example of example. Example, did I call it example? Yeah, example of example. So you see actually that's something down to earth. G being SL2, my favorite example, F being QP, and S being, which I call G prime, being corresponding to these matrices A, B, P, B, A, with determinant equals 1. So in that case, well, we have the character phi and phi. So a character A, B, P, B, A gets mapped to phi of 2b. And so now we have to extend this as far as possible. So what is K in that case? K, as I said, it's S of f times gx. So that, sorry, in that case, r is 1/2 the depth. So I have to take here depth 1/4. And so if you have done your exercise, you'll see, well, this is just a matrices of this shape. Determinant, well, I will stop writing determinant equals 1. You can do that yourself. Times this 1/4 filtration subgroup looks like matrices of that shape. 1 plus PZP on the diagonal, ZP in the upper right corner, PZP in the lower left corner, and determinant. Okay, I said I stopped at one board. So that's how these two groups look like. And so what is actually the product? So when you sit down and work out what the condition determinant equals 1 means, you actually realize that just working it out, A has to be of the form plus minus 1 plus something in P times ZP, and B has to lie in ZP. So actually, it turns out that almost all of this matrix lies already in here. So this is actually just equal to plus minus the identity, plus minus the identity times actually this subgroup here. And now I really stop writing determinant equals 1. You can do that yourself. So this is what this group is. So what we need now is to extend this character phi to character phi hat on here. And so what does phi hat do? Phi hat now takes a matrix in there. So it takes a matrix A, B, PB, no, not PB, PCD. Sorry, just a random matrix in here, where A and D, they have to be of the form 1 plus PZP or minus 1 plus PZP. And it sends it to, well, we need to somehow extend this character. And one way to extend it is to send it to P plus C. And then apply this additive character phi. Yes?
Should K be S of O?
K be S of F sub O. It should be, strictly speaking. So the question was, should K or should that be?
Should that be S of O?
So the question is, should that be S of sub O? And the answer is no, it shouldn't be sub O, but it should be sub X, but this is automatic in that case.
I think the question was S of O, the integer.
Oh, no. So yeah, that's the other. So no, it should be really F here, but so S of F is equal to these matrices A, B, P, B, A inside SA2 of F. Well, F is QP. And then it turns out by the determinant condition that actually A and B, they lie in O. O being ZP. So actually this is compact and these entries, they lie in O, but we don't require it. So this is just by working out what it means so determinant is equal to 1. Yes?
How do the quarter come in expression in this?
How do
the quarter, the 1/4? How do you see it?
So I didn't hear how that, oh, the 1/4. How does that come into the game? This is equal to R/2, and R was 1/2.
Yeah, but in evaluating this subgroup, did you use this 1/4 in order to? In
order to define that group, and it turns actually out, so for those who have done the exercise that I gave you last time, in this case, gx 0 plus equals gx 1/4 equals gx 1/2 equals, well, these matrices. 1 plus CP, 1 plus, well, I'm not writing it down. That was your exercise, this matrix. So in that case, it doesn't matter actually which of these you take. They are all the same, and at 1/2 plus is the next interesting thing that happens. Yes?
So where is the minus identity coming from?
The minus identity is coming from the fact that if you work this out, there are a lot of exercises here. If you work out what the conditions on A and BP are, you will realize that in particular, A is equal to plus minus 1 mod P. And that's why the only thing that's interesting is plus minus 1, and the rest is already contained in this part. All right.
And are you
Any-
claiming that such hat phi is always uniquely extended, or it's up to choice?
I say that, well, there's a very precise way you can, I don't claim it's unique, but I say we choose a particularly nice one by saying, by making it trivial. The rough way is to say you make it trivial on the root groups outside S. And I've written up in the notes very precisely what that means. So the question was, is this phi hat unique? And I said, well, not necessarily. We have a precise way of defining it so that everything else works, which is by making it trivial on root groups outside S.
What happens without this assumption?
Without what assumption?
The R half equals R half plus assumption?
Without the assumption, if I had half an hour more, I would tell you.
That's when you use the identification.
So yeah, I will tell you. So when this is not equal here, then the general construction will use the theory of the Weil-Heisenberg representation, and then thinks that this will not be a character, but a higher dimensional representation. I'll hint at that in a bit. Or I'll do that in a moment. And I write it out explicitly in the notes for those who are interested in it.
P is replaced by some unit.
P is replaced, so sorry.
Only happens when this quadratic extension is unrelated.
What happens? So the question is, that happens when the quadratic extension is unramified? What happens? No, nothing. It's even ramified in my case. I add a square root of P, so that's ramified.
He's asking whether the case where assumption does not hold, is it the when E, when it's 100?
No, because R could be 2, and then R over 2 is, So there was a question if something can only happen when it's unramified, and I don't know something that happens only in, well, I know things that happen only in that case, but I don't see anything of interest right now. All right, so then, let's see, where am I actually time-wise? Up. So that was a special case. Now let's do the general construction a la JKU, well, maybe with a twist. That appeared in a paper with Kalitha and Spice. So KS stands for Kalitha and Spice. So how does the general construction go? So the input for the general construction is the following. It's a tuple consisting of 5 things. The first thing is a sequence of twisted Levy subgroups. So we have our group G, and that contains a smaller group G2, a smaller group G3, and so on up to Gn, and the last one I call Gn plus 1. So that's my way of indexing things. U indexes them by upper numbering and has the reverse order. Each has their advantage. And we assume such that the center of Gn plus 1 is anisotropic. In general, you would look at the center of Gn plus 1, not the center of G, but I assume the center of G is finite. So for example, it could be a 2-step where G is equal to G1, and this is just the torus that is elliptic like we have seen above. So in the general case, we don't just have a 2-step, but we have an n-step, n plus 1-step situation. Then, well, we take a point inside the building of Gn plus 1, which is the vertex inside this building. And then we take a depth 0 representation contribution. So we take rho and irreducible representation of Gn plus 1, the smallest one, sub x, so the stabilizer of x, that is trivial on Gn plus 1 x0 plus, and the restriction to Gn plus 1 x comma 0 mod Gn plus 1 x0 plus, our reductive group is cuspidal. So in other words, this is just, as you have seen above, the input for a depth 0 representation of Gn plus 1. So depth 0. In other words, we take a depth 0 representation of Gn plus 1. That's what we really do. So I said general representations are made out of two things, a depth 0 piece and characters of higher depths. So the higher depth piece will be the characters, so that's 4 will be just the depths of the characters, so I call it R1 greater R2 greater Rn, which is greater than 0. In some sense, 0 is the depth of this last piece with the depth 0 representation. And then the fifth piece are now the characters. So these are some characters phi I for I between 1 and n, which are is a gi plus 1 generic character of gi plus 1 of f of depth Ri.
Are these GI twisted Levy?
Are these two? Oh yeah, I should have said this. I didn't write this. These are twisted Levy subgroups. Thank you. The question was if these are twisted Levies, and yes, that's the excellent comment. That's what I meant to write, but I thought I saved time, but not that way. So you have a twisted Levy sequence. They split by default over the same extension because P doesn't divide the order of the Weyl group. Then you have the depth 0 input for the smallest one and characters for all the others.
In this example, you are dealing with a semi-simple case of general reductive case.
Yeah, throughout G is semi-simple. G is semi-simple. Otherwise, you would have to quotient out by the center of G here. You don't have to if you assume G is semi-simple.
Does it matter whether you ask the GIs to be twisted Levies of G or of the previous one, like sequentially?
That's automatic. Yeah, it's the same. It's the same. The question was if it's a twisted Levy of the whole or of the previous one, but it's the same. All right. So that's the input for the general construction. And let me call this a U datum. I think that's what people started using as the notation. And so then from the U datum, what you do is you construct a compact open subgroup K as before. What is K in that case? In that case, K is equal to, now we just do the same for all these groups. So we take G1 at x of depth R1 over 2, G2 at x at depth R2 over 2, and so on and so on. And so on, up to the last one, Gn at point x of depth Rn over 2. And then you add the depth 0 piece for Gn plus 1. So there you take just the stabilizer of x. So that's a compact open subgroup you work with in general. And then the general rho, I should call it rho tilde now, the general thing that we induce is defined to be rho tensor kappa, where rho is just an extension of this rho. So rho is defined on here, and you just set it trivial everywhere else. So you just extend rho. And what is this kappa? So this kappa is constructed from the phi i's. And so that's a generalization of the example over there, how we constructed it by extending. But in general, it's constructed using the theory of so-called Weil Heisenberg representations. And the reason why you use it is precisely the answer to the question I was asked earlier. You first extend the character as much as you can, but then if we don't have equality here, then to go from the R/2 plus piece to the R/2 piece, you have to invoke the theory of the Ray-Heisenberg representations. And this construction here, that's the construction by you. But you might want to actually twist everything. I like to twist things. Plus a twist. And so what is the twist? The twist is just a map epsilon from k to plus minus 1. That makes everything nicer. By which I mean that things fit much nicer in the local Langlands correspondence and much more. A lot of intertwining statements hold, and so on. I'm not defining this epsilon for you here. You can look at that paper, but it's not doable in a few minutes. And then the claim is then theorem, the compact induction from k to g of f of rho tilde, or if you like, also twisted with epsilon, if you want to include the twist. But this statement holds also without the epsilon, is an irreducible supercuspidal representation. Irreducible supercuspidal representation. And under our assumptions, all irreducible supercuspidal representations arise in this way. And I guess I should put names here. Let me put names you and Kim. So you suggested the construction. Julie Kim proved exhaustion under some nice circumstances. And now we know that this is actually providing us with supercuspidal representations, and all arise in that way under just the assumption that, let me recall, P doesn't divide the order of the Weyl group and G is tame.
You didn't talk about the construction, but is it some kind of tensor product? Or?
Yeah. So this kappa is a tensor product of kappa i's, and each of the kappa I is essentially this extension, and then you use the Ray-Heisenberg theory. That's roughly it. I'm happy to give more details later, but it would take another 10 minutes or 15 minutes to do that. And, well, there's a limit of time that I've been given. But there's also Q&A if you want to see details.
What is the depth of the representation?
The depth of the representation is the R1 here. The question was, what is the depth? All right, that's great. So we have all representations now. So then the next question is, well, how unique is it? Like taking two different inputs, can we get the same representation or not? And well, that was studied by Hakim and Murnahan in 2008. And I should also put Tasha Kaletha's name here, since he removed an assumption that they had to make. And they give you precise criteria when two inputs give you the same representation. So they say that two U data, say GI, X, rho, Ri, phi I, and the same with the prime, X prime, rho prime, Ri prime, phi I prime, yield isomorphic representations if and only if one can be obtained from the other by a finite sequence of the following operations. And there are three operations you can do. The first one is you can replace rho by rho tilde, which is isomorphic to rho. Well, if you replace it by an isomorphic representation, you get isomorphic representation, so that's not surprising. The second thing is not surprising either, which is just conjugation by g of f. So you can take the whole input and conjugate it by an element in your group. It's the same as what I said at the very beginning. If you take a torus and a character and conjugate this by an element in the group, you will get isomorphic representation. And the third condition is, the third condition is that you can replace rho by rho tilde and the phi i's by phi I tilde, such that, roughly speaking, let me put this in quotes, such that if you take rho tensored with all the characters, the product over the characters, then this should be equal to rho tilde tensored with the product of all the other characters. This equation here doesn't quite make sense because these objects are defined on slightly different groups. So you have to actually specify precisely where you define things. But one can make that statement precise, and I've made this precise in the notes if you're interested in it, and that's called refactorization. So it just means you take the product and decompose it as a different product. Well, you have to be a bit careful with doing that. And that's all you can do. So that means we have now a parametrization of the supercuspidal representation. We know that all arise from such a datum, and we know which two data give us the same representations. Let me swap that. Might be easier to see. All right, that's great. So here we are. We have all yeah.
The numerical R1 so does not vary.
The numerical R1. Oh yes, that's so. So the question was the numerical R1 doesn't vary. So in particular, this means that this theorem implies that Ri is equal to Ri prime all the time. So that's an invariant. That cannot be changed. And all the other things, yeah. And also, well, X can be only changed to conjugate of X, and the same with the groups. So the groups are fixed up to conjugation. All right, so time to breathe. Here we are. We have all the supercuspidal representations constructed from an explicit datum, and we know precisely which representations are the same. So I think I've done now part 1, construction, part 2, classification or something like that in my title. I forgot my title. The last part was character formulas, so I should head towards character formulas for the end. And for that, I want to go back to where I started. I started this talk series with telling you about discrete series, having character formula, and then these mysterious regular supercuspidals having the same character formula. So I should tell you now, what are these regular supercuspidal representations? Let's see, we started 5 past or something like this, so 25 is good. All right, so definition. I'll give you the definition I owe you for a long time now. So S comma theta is tame, well, in our case, everything is tame, elliptic regular pair, if the following happens, if S is maximal elliptic maximal and elliptic maximal torus of G, and well, split over tame extension, but that's automatic, but I want to give it a name, so say split over some tame extension E over F being a tame extension. So that's S. What is theta? Theta is the character of our torus that satisfies two conditions. The first one is the following. I define for you phi sub 0 plus a subset of the root system phi of our group with respect to S. Again, I mean always absolute roots, so that's the absolute root system. And I define this to be all those roots such that if I take the norm from E down to F of alpha check of E0 plus, then this should be, then evaluate theta on it, this should be equal to 1. So we call this zeros filtration subgroup here. This is just 1 plus pi E times OE. So this is a subroot system. This actually corresponds to a twisted Levy subgroup. It's the root system of a twisted Levy subgroup. And the requirement is that then we want that pi 0 plus contains a system of positive roots. Well, so far that's obviously the case, but that is preserved under inertia. That is preserved under the inertia subgroup I inside the Galois group of the field F. So that might look a bit odd. What is this condition actually saying? If you take the group, the twisted Levy subgroup attached to 0 plus, and base change to the maximum ramified extension, to a maximum ramified extension, then the statement is saying that over this maximum ramified extension, S should be a maximally split torus. And that has as a consequence that inside the reductive quotient of gx0 mod gx0 plus, where x is the point attached to S, S actually corresponds to maximal torus inside there. So S will give us a maximal torus inside the reductive quotient of the group attached to this 0 plus subsystem. And then the second, so that's a bit technical. The second condition is that we require now, we look at our character, and, oh, sorry, I should now let me give this thing a name. So I said it only in words, so this 0 plus corresponds to some twisted Levy subgroup with root system of G prime being the 0 plus. And then the second condition is that if we now restrict our character to gx0, where x is the point that, well, x is equal to the building of S. S gives us again a point in the building. Oh, sorry, maybe I just want to restrict also to S to make things easier. It's not defined there yet, so that doesn't even make sense. So this is a priori only, sorry, this is only character of S, so I can only restrict it to S0. And I want that this should be, well, somehow as generic as possible. What does it mean to be as generic as possible? It means that the stabilizer of this character, well, where do I look at the stabilizer? So it's a character of S. So I only look at the stabilizer inside the normalizer of S, inside this, well, G prime or G, doesn't matter. And I want the stabilizer to be as small as possible. And what is the stabilizer? Therefore, it has to be S of S, because, well, the torus itself stabilizes the character. I mean, if you conjugate with something in it, the torus is commutative, nothing happens to it. And we want that nothing else preserves the torus. So in other words, any other element, if you conjugate the character by it, you get a different character. So it's just somehow as regular as you can imagine. So that's the notion of a elliptic regular pair. All right, and now what we need to do is we have this elliptic regular pair, and we want to construct supercuspidal representations from it. Well, we know how to construct supercuspidal representation. Just give such an input, and then we perform JKU's construction. So what we need to do is take this and construct that. So how do we construct the representation attached to S and theta? Well, we start with our tame. So in words, we start with our tame elliptic regular pair S theta. And then from there, we want to construct the U datum. And then from there, we know how to construct the irreducible supercuspidal representations. So that's just use construction plus a twist. So all I have, so this is what I've already told you, or hand waved about. So this is the thing that we need to do. And well, how do we do that? Well, X is rather the X is just the building of the elliptic torus S, which is a point. So that's how we get our point. So that's part 2. Well, what else do we get? We need this twisted Levy sequence and the characters on the depths. And so this is actually the so-called Hauer factorization introduced by Hauer, I think, for GLN, and then Kasha-Kalefa generalized it, which means that actually we can write theta as a product phi 1 times phi 2 times phi 3 times, well, phi n times phi n plus 1, a product of characters that are determined by basically looking at where the so let's see. We defined here some subsystem by looking when there's a character evaluated at the co-characters equal to 1 when we plug in the depth 0 plus. And now you can play the same game and plug in all the different depths, any different depths you like. And thereby you can somehow figure out how to split up the characters. And at the same time, then you get also the depths with it R1, R2, and so on. Greater Rn, greater 0 equals Rn plus 1, just by looking at where do jumps happen, where do interesting things happen. And together with this, you also get the twisted Levy sequence. So this is a bit sketchy, I admit. I'm not writing out all the details, so this is just a rough sketch that there is a way to start with a character and somehow decompose it into rather regular pieces from which you get the depths and these groups. And you can do this explicitly by using a formulation like that with different depths other than 0. Which has then the properties that these phi i's here are gi plus 1 generic of depths ri. And these gi's, these are twisted Levy subgroups. No, gn plus 1 contains S. It's not necessarily equal. The question was if gn plus 1 is equal to S, and I said it contains S. So if you look up, we basically have everything except for the depth 0 piece is missing. And so that's the big mysterious thing. And where do we get the depth 0 piece from? Well, there's one piece of information that we haven't really used yet, which is this weird phi n plus 1. And this last character, this phi n plus 1, so this is it's of depth 0. And this actually provides us, so this provides us with a character, let's call it phi n plus 1 bar of, let's call it S bar of a torus S bar inside the reductive quotient Gn plus 1 x0 mod Gn plus 1 x0 plus. So this is constructed from S, this is constructed from this character, and moreover, this character is a character that is in so-called general position in Deligne-Lustig theory, so general position following Deligne-Lustig. And, okay, bad blackboard work. So let me continue over there. And from Deligne-Lustig theory, that means that we can construct a representation which they call plus minus RT S bar phi n plus bar. So Deligne and Lustig provided us with a way to construct a representation which has this funny name here, which is a representation of gx0 that is trivial on, oh sorry, gn plus 1, gn plus 1 x0 plus. And now we just extend it to get rho. And then rho is an extension of this one. So this is very impressionistic. I understand that. This is just to give you just a feeling for how things work. The details are a bit more complicated. But the rough idea is start with an elliptic torus and a character. And then just by looking how we can somehow peel off pieces, we decompose this into a bunch of characters that give us these twisted Levy subgroups. And the last piece then gives us, via the Deligne-Lustig theory, this regular representation. I'll write some notes in which I will explain that a bit more, but also you can look at Tasha's original paper for the details. So this is just giving you some impression for how things work. All right. Final 7 minutes for the final topic, which is characters, character formulas. So I was asked to tell you a bit about characters, and that's why I needed to introduce the pelagic representations, the regular supercuspidal representations, because we only know the character in that setting, a slightly more general, but so let me put down some names. I was asked to put down names, so let's see if I get them together. So there are a lot of people have worked on the character formulas, building up on each other in a more and more general setting. So I just order them alphabetically. Jeff Adler, Stephen de Backer, Mark Reeder, Lauren Spice. Does R come before S? Yes. And Spice, yes, a lot of papers on that. And I guess the final statement is well, now it's no longer alphabetically, but that's fine. That's just where the final statement appears. And well, Tasha Kaletha, I guess I should put him, well, he's quite often on the board. Forgive me, Tasha. So Tasha has studied special cases, but these people have extensively studied all kinds of versions of character formula. And so the final character formula, now I need to assume that f is a finite extension of QP, that P is very large. I can make that precise, but it's large. So that very large and finite extension of QP, this will guarantee that the exponential map exists. That's why I'm doing that. And then here we go. Here's the character of an epipelagic representation and of a regular supercuspidal representation attached to S and theta. So S theta now is a pair as there. It's a tame elliptic regular pair. And then we get the representation, and then we want to figure out what the character is. And so what is the character? We evaluate at an element gamma. What is gamma? Well, the character we learned last time, it's a priori a distribution, but there's this big theorem of Harish-Chandra that it's actually represented by a function defined on the regular semi-simple elements. So gamma is an element of our group that is regular semi-simple. And now I want to write gamma actually using the Jordan decomposition. So I write gamma as, let me write this below in case I run out of space there. I write gamma as gamma 0 times gamma 0 plus, where, what are these things? Gamma 0 is the topologically semi-simple part. So that means that the order of gamma 0 is finite and co-prime to P. So that's what we have seen last time. Last time I gave you the character formula only for gamma 0, and someone asked, well, what is it in general? So here's the answer to the person who asked, and to the organizers who forced me to talk about it. And gamma 0 is topologically unipotent, which means that if we take the limit of gamma 0 to p to the n for n goes to infinity, then we get the identity. And so this decomposition here, that's the topological Jordan, however it's called, Jordan decomposition, and that's due to spice in a rather general setting. So you can decompose every element uniquely like that. In general, you have to do it mod center, but since I assume semi-simple, it simplifies things. And here we go. I have 2 minutes to write this character formula. What is in there? We've seen last time the Kottwitz sign of G. Now there's a Kottwitz sign of J as well that wasn't there last time. What is J? J is, I'm optimistic with spacers. Let me clear this blackboard for auxiliary things. J is the centralizer of gamma 0 connected component. So last time we had gamma equals gamma 0, so that was disappearing. Then we have the root number as last time of the characters of minimal Levy in a quasi-split group as in the inner form of G minus, well, for G minus the same now for J. And phi was our additive character, so that's the root number. It's just the fourth root of unity. Well, just. Then we have the discriminant to the minus 1/2 that we've seen last time, and now we have a big sum. Where do we sum over? We sum over all the elements G inside our group, such that if we conjugate gamma 0, we end up inside the torus. So that's as before G gamma 0. G inverse. And well, we mod out by the things we need to mod out. So if we conjugate something in S by S, nothing happens. And on the other hand, if we conjugate by the centralizer of gamma 0, nothing happens. What do we sum? So we first have what we have seen last time, the root number attached to some auxiliary data and A data and the chi data, evaluated at gamma 0, G times gamma 0, sorry, the G conjugate of gamma 0. Then we have the character evaluated as G times gamma 0. That's what we have seen last time. So far, that's what we have seen last time. Now we only need the contribution of the 0 plus piece, and that's via an orbital integral. So the last piece, since I don't know if you can see it there, let me write it here. The last piece is the Fourier transform of an orbital integral with respect to work with the group J, or its Lie algebra, of an element X acted on by G. This element X, I need 1 minute to define X. X is defined as follows. We require that we evaluate the character at the image of a y under the exponential map for y being in G0 plus and the union of all the Gx 0 plus. Then this is given by pairing this element y with the element x. So x is an element in the dual of the Lie algebra such that we pair with y and then apply this phi, we get the character. So it's just a way to basically express the character on the Lie algebra. We move here to the Lie algebra.
What does it say before the theta? What are the, no, there's a theta there in the formula.
There is a theta in the formula.
The formula in the sum. Upper G is gamma. So
Before that, it's a gamma.
Upper G of gamma naught, and what do you apply here?
Okay, I would have been finished on time. All right, so this is the absolute transfer factor with the decoration 2 of an A datum and a chi datum, which I haven't told you how to construct these, and then evaluated at G of gamma 0. And then, so that's the same as what we've seen last time. Then the character evaluated at the gamma 0 piece. And then the missing piece is the gamma 0 piece. And this enters through the Fourier transform of an orbital integral. So that is, strictly speaking, the Fourier transform of an orbital integral is a distribution. So that's a function representing it. And, well, and that's it. That's the character formula, and that's my talk. Thanks. Oh. Sorry, I forgot the log there to go down to the algebra.
Okay,